Good afternoon. Myself, Dr. Rambabu, working as Assistant Professor in the Department of ECE. I am from B.V. Rao Institute of Technology, Narsapur. Here I am dealing with the course name called Microprocessors and Microcontrollers. Our today's topic is Register Organization of 8086 Microprocessor. Before we are going to discuss different registers of 8086 microprocessor, first let's check what is the learning objective of this particular topic. The students will be able to understand the function of various registers in 8086 microprocessor. This is the main learning objective of this particular topic. Right. Now, let's start with the register organization of 8086 microprocessor. In the last session, we discussed about the internal architecture of 8086 microprocessor. That's called the functional block diagram of 8086 microprocessor. We already observed in bus interface unit and execution unit, there are many registers are placed. In this session, in detail, here we are going to talk about what is the function of each and every registers. Totally, our 8086 microprocessor contains the 14 registers are there. These 14 registers are classified into different sections. That is, first one is general purpose registers, and second category is index register, and third category is status and control register, and fourth category is the segment registers. And another important thing is the size of the each register. Here it is the 16 bits. That means it can able to store 16 bit of data. Now let's check the function of each and every register. First we'll start with the general purpose registers. Here we can check general purpose registers are, here it is showing AX, BX, CX, DX. These are all the general purpose registers. And index registers are BP, SP, SI, DI, and status and control registers are flag register and IP. And another category, that is segment registers, that is the core segment, code segment, stack segment, data segment, and extra segment. Right? That is the CS, SS, DS, ES. Here AX stands for accumulator, BX is base register, and CX is count register, DX is data register, here BP is base pointer, stack pointer, source index, and destination index. Here this IP that stands for, that is the instruction pointer. Now, first we'll start with the general purpose registers. Before we are going to talk about the general purpose registers of 8086 microprocessor, first we'll check the programmer's view, the programmer model of 8086 microprocessor, how the registers are placed in the internal architecture. As we know that the total internal architecture of 8086 microprocessor, that is divided into two units. One is the bus interface unit and second one is the execution unit. Bus interface unit that contains some register, some set of registers, and execution unit that contains some set of registers. Here that is the extra segment, code segment, stack segment, data segment, instruction pointer. These are all the part of bus interface unit. And accumulator, base register, count register, data register, stack pointer, base pointer, source index register, and destination index. These are all the part of our execution unit here. Now, let's talk about general purpose registers. The name itself, it shows here we are using these type of registers in general purpose usage. That is here as I already told you, each and every register size is, that is the 16 bit here. Again, these registers, that is the AX, BX, CX, DX, accumulator, base register, count register, data register. These registers are again, that is the divided into two parts. That means that is split into two parts, that is the lower byte and higher byte. That means 0 to 15 here it is showing, 0 to 7 here we are calling the lower byte register, and 8 to 15 here we are calling the higher byte register. Let's check, for example, if you can take AX is the accumulator, the AX again that is divided into AX register higher byte, that is the 8 bits, and AX register lower byte, that is the AL register here. For example, if you want to perform the 16-bit operations, here we have to select the AX, BX, CX, DX. For example, if you want to perform the 8-bit operation, there we are going to select any two 8-bit registers. Similar way, the BX register that is divided into, that is the BX register higher byte, BX register lower byte, and CX register again divided into CX register higher byte, CX register lower byte. and DX register higher byte, DX register higher byte, and DX register lower byte. In that way, the architecture contains the registers are divided into two parts, like higher byte of register and lower byte of register. And depending on our operation, sometimes we are going to select the 16-bit register, and sometimes here we are going to select the 8-bit registers. Here normally, I already told you, normally here we are using this type of general purpose register to store the temporary results. Suppose if you want to perform any arithmetic operations or logical operation, to store the temporary results, here we are using this type of register. And I already told you, that means the size of this each and every register, that is the 16 bits wide. And it can be accessed either 16-bit or 8 bits. That means sometimes, suppose if you want to use for 16-bit operation, there we are using the AX, BX, CX, DX register. And for 8-bit operation, there we are going to use the AH, AL, BH, BL, CH, CL, and DH, DL. Any two combination of registers you can use for the operations. Now, here we are going to check the each and every register operation in detail. Here AX register, I already told you, that is the AX is the accumulator register. It is preferred register to use the arithmetic and logic operations. At the same time, it is used for the data transfer operations, and it must be used in multiplication and division operation. And AX register definitely, while you are performing the 8-bit operation or 16-bit operation, AX register is the default register. And also AX register can be used in the input and output operations. And BX register is a base register, and this BX register most of the time here we are using to serve the address related storage. For that, this base register also called as the address register. And another important register is the count register. CX here usually we can call as the count register, and most of the time this count register here we are using it to store the count value. That means while you are performing the shifting operations and rotating operations, here to store the counting value, how many times we have to shift the bits to the left, how many times we have to shift the bits to the right, and number of times the bits to be rotated. The count value here we are going to store in the CX register only. And another important thing is the CX register here we are using for the loop operations. For example, how many times the iteration must be done. For example, 2 times or 3 times, that particular count value here we are going to place in the CX register. And another important register is the DX. DX register also called as the data register. This particular data register can be used in the multiplication and division operations. And this while you are performing the 16-bit multiplication operation, that while we are performing one 16-bit number multiplication another 16-bit number, the result may be 16-bit into 16-bit. Sometimes the result may be 32-bit number. Here we are having the only 16-bit register. This 16-bit data in 16-bit register we can't able to store this 32-bit result. At that time, here we are going to store the 32-bit result in two combinations of register DX and AX. Higher 16-bit 16-word data stored in the DX register, lower 16-word data result that is stored in the AX register. In that way, here we are going to store we are going to use the DX register for the arithmetic and logical operations. At the same time, this DX register also here we are using for the input and output operations. Next, the other category of registers are pointer and index register. Here mainly we are having the 3 pointer registers are there. That is the stack pointer, base pointer, that is the next one is the instruction pointer, and 2 index registers are there. That is the source index and destination index. And most of the time this pointer registers and index register here we are using to store the offset address. To store the offset address, here we are using this pointer and index registers. Here I already told you that is all these pointer index registers are 16 bits wide. Here just like our general purpose register, there is no possibility to split these registers into lower byte and higher byte. And this is the mostly we are using for the memory pointers, the address related operations to store the offset address while you are performing that is the memory organization, memory segmentation, while you are accessing that particular data. There we are going to use this offset registers. Here the one example here it is showing move AH comma, that is the SI. Here what's happening here? Move the byte stored in memory location whose address is contained in the register SI to the AH register. SI is holding the offset address. The offset address is holding some data. That data here we are moving into the AX register. In that way, here we are going to use this index register at the same time pointer register. And another important thing is the stack pointer, base pointer, source index and destination index. These are all the control of the programmer. But if you can see, the IP instruction pointer is not under the control of the programmer. This IP is under the control of the processor only. Whenever the processor is going to execute some set of instructions, here before though that is going to execute the first, after completion of the second instruction, here to execute the second instruction, to load that particular address, next instruction address, here we are using the pointer register called the instruction pointer here. And another set of another category of registers are, that is the 4 segment registers are there. That is the code segment register, data segment register, stack segment register and extra segment register. Here, these 4 segment registers, here we are using to store the base address or starting address of the segment. Here, the total 1 MB memory space that is available for 8086 microprocessor, that is divided into 16 equivalent logical segments. Here we are defining the 4 segments. Those 4 segments are, that is the code segment, data segment and stack segment and extra segment. The each and every segment size, here it is that is the 64 KB. Here that is, for example, if you can see, this is the total segment. In this particular segment, each segment is having a starting address and that is the ending address. This is the bottom of the segment and this is the top of the segment. Each and every segment size, here it is that is 64 KB. To store the starting address, or we can call that is the base address. Here, for example, if it is a data segment, to store the starting address, of this particular data segment, here we have to use the data segment 16-bit register. For example, here it is a code segment. To store the starting address or base address of the code segment, here we have to use the code segment 16-bit register. Similarly, for stack segment, at the same time, extra segment also. Right. Let's check that is the combination of segment, that is the segment register, that is to store the base address, at the same time default pointer register. What are available? Those things now here we are going to check. Right. Here, for example, here this particular table shows the first column, that is showing the segment part. Each and every segment, here 4 segments here it is showing, that is the code segment, data segment, extra segment and stack segment. Each and every segment size, here it is, I already told you, that is the 64 KB. In that 64 KB, to hold the base address, there must be one default register must be there, that is the CS. Here it is that is the code segment register to hold the base address of the 64 KB code segment. At the same time, offset address. For example, this is the starting address. For example, somewhere here we want to access this particular data. The distance between the starting memory location, at the same time our required memory location, this particular thing that shows that is the offset address. To hold that particular offset address, here the default pointer register or offset register is available, that is the instruction pointer. Similarly, for example, if you are using the data segment DS is the data segment 16-bit register and source index is the offset register. To hold the offset address, there must be the source index register. And for example, we are accessing the data from the extra segment. For the default 16-bit register, here it is to hold the base address, that is the ES is the extra segment 16-bit register. To hold the offset address, here we are using the destination index register. At the same time, for example, if it is a 64 KB, that is the total memory space. To hold that base address, here we are using the stack segment. To hold that is the offset address, there are 2 registers can be used. One is the stack pointer, at the same time, this is the base pointer. Those 2 registers can be used to hold the offset address of that particular stack segment. Here, Another clarity here, this particular segment size is the 64 kb and segment register size is this is the 64 kb and this is the 16-bit register, and offset register here it also, that is the 16-bit register. This is the usage of the base register and offset register in the memory segmentation. Now, let's discuss about another important register in our 8086 microprocessor, that is the flag register. To know the status of the operation, whenever we are going to perform some type of arithmetic operations or logical operations, definitely our processor we have to know the status of the operation. That means whether the carry is generated or not, whether the result is 0 or non-zero, whether the sign is that is a positive sign or negative sign, even parity or odd parity, if any overflow occurred or not, the interrupt is enabled or there is no interrupt. For example, there is a single step interrupt, there is a direction, there is a upward direction or downward direction. In that way, to know the status of the operation, one more important register is there in our 8086 microprocessor, that is the flag register. The size of the flag register here is also 16 bits only. Now, let's check what is the operation of this particular flag register. Now, the size of the flag register here, it is the 16-bit wide here. That is the here bit 0 to bit 15. Totally 16 bits are there. Here totally, if you can see, this is a bit format. This is a flag register bit format. In that, even though the size of the register is the 16 bits, only 9 flag bits are defined. 9 flag bits are defined. Remaining 6 flag bits are undefined. Here the cross that shows the undefined flag bit, and remaining all mentioned flag bits are, that is the defined flag bits here. Now we are going to check what is the each and every bit, what it shows here, and what is the operation of this particular flag bit. For example, here we can say the first one is the overflow. While we are performing any arithmetic operations, for example, one 16-bit number or multiplying another 16-bit number, suppose if the result gets overflowed, this particular flag bit goes to 1. Suppose if there is no overflow, this particular flag bit goes to 0. And next one is the direction flag bit. While we are accessing the data, especially in the string related operation, for example, if you want to access the data from the higher memory location to the lower memory location, the DF flag bit goes to 1. For example, lower memory location to the higher memory location, for example, the DF flag bit must be the 0. In that way, here we are going to use the direction flag bit. Here, another important is the interrupt enable bit. For example, while we are working with the 8086 microprocessor, sometimes the interrupt may be generated, there may be hardware interrupt or software interrupt. If any interrupt is generated, that is the interrupt flag bit goes to 1. For example, if there is no interrupt, this flag bit goes to 0. And similarly, next one is the trap flag bit. In this, you can also call this single step interrupt here. Each and every line of programming execution, one interrupt will be generated. To know the status of that particular program execution, that particular interrupt we can call as the trap interrupt or single step interrupt. And next one is the sign flag bit. For example, while you are performing the operation, sometimes the result may be positive result or sometimes may be negative results. Here, this particular sign flag bit that represents the positive sign or negative sign. And next one is the 0 flag bit. This 0 flag bit is whether the result is 0 or non-zero. This can be identified by using this particular 0 flag bit. Next one is the auxiliary carry. AF flag bit that shows the auxiliary carry. For example, while you are performing the BCD operation, if any carry is generated from the 3rd bit to the 4th bit, that particular carry usually we can call as, that is the auxiliary carry flag bit. Next one is the parity. While we are performing some type of error correction detection method, here we have to consider some parity also. Sometimes even number of ones or odd number of ones that can be recognized by using one of the flag register, that is called the PF flag bit. This is the parity flag bit. And last one here it is showing that is the carry flag bit. While you are performing any type of arithmetic or logical operation, suppose if any carry generated the MSB side, that is the most significant bit, usually we can call as that is the carry. There is a carry, there is no carry, the processor can be identified by observing this particular flag bit here, right? Here and summary, here totally the defined 9 flag bits, 6 are the status flag bits like carry flag bit, parity flag bit, auxiliary carry, that is the 0 flag bit, sign flag bit, overflow. These are all comes under status flag bits, and the remaining flag bits are that is the 3 control flag bits. What are those? That is the direction flag bit, interrupt flag bit, trap flag bit. These 3 flags are comes under the control flag bits here. Now, this is about the total register organization of 8086 microprocessor. After completion of this particular topic, after learning this particular topic, students will be able to use the knowledge of this register organization in writing of the assembly language programs. And students will be able to understand the operation of 8086 microprocessor in detail. This is about register organization of 8086 microprocessor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.